use this. Oh, can people hear me now? Or can people hear me now? There. All right, that'll work. So when I put together the title of the talk, I was just trying to figure out what I wanted to talk about around type classes. Now, this has been a fight I seem to be fighting over and over again on Reddit and different media. Let me make sure I actually have this thing recorded. If not, you have it. And I wanted to just be able to put everything I wanted to say kind of in one place. And we were originally going to do this, I think, about 3 months ago, and I was perfectly prepared. I had all of my ducks in a row. I was all set to say everything that I wanted to say about type classes, and then 3 months passed. So I think I remember almost everything I wanted to say about the topic, and we'll see how it goes. I'm more than happy to throw this open to the room if folks have questions, want me to drill in deeper, want me to slow down, explain things more. We have plenty of time. We have the whole, the couple hours here. And we're going to do some talking about like what we want to do for this coming year afterwards. So, we don't have to. We're not going to fill 2 hours with me ranting about type classes.
Unless we stop and slow you down.
Unless you stop and slow me down a lot. So I stole a Scott Pilgrim poster because it seemed appropriate. But I did not take Dan Dole's suggestion that I should give the description from, what was it, Ion Storm, what was the?
Oh, yeah.
The Ion Storm ad?
The famous John Romero one?
Yeah, the John Romero ad of John Romero will make you his, but I did take this one. So what I want to talk a little bit about is the history of where type classes came from, what they are, why they're different from what people have in other languages, and we'll go from there. And sort of the history of type classes is very tightly tied to the history of Haskell itself. And really they're not what you expect. The name type classes makes people think that they're about classes in OOP. But they're their own beast. They're actually quite remarkably different. And if we go back to the sort of original working group, this should be a photo from, I think, 1987 from the original IFIP working group on functional programming. You can see Simon Peyton-Jones, much younger looking there.
Oh, yeah.
Hudak. The rather certain individual in the back there is Philip Wadler. And he came up with type classes by misinterpreting someone. He was talking to Joe Faisal after a working group meeting. And so Haskell itself was designed in the late 80s. And it was designed by committee because what was happening was a lot of people were working on functional programming and particularly about laziness in functional programming. And they wanted to be able to collaborate or at least write papers and talk to each other. But what would happen was you would have to basically write your language, write your paper about your language. And then by the time you were done, you'd get to the last couple of paragraphs and you'd have a little bit of room to talk about the feature it was that was interesting. The thing that you wanted to say only had a couple of paragraphs worth of room to be talked about at all. So they got together and they said, let's try and standardize on a programming language. And there was a programming language that was pretty much universally liked at the time called Miranda, which is very much, if you look at the surface syntax of Haskell, there's a lot of similarities from it to Miranda. But when they approached the guys at Research Software Limited, which was selling Miranda to universities at the time, and they asked, yes?
He's on the far right of the photo. He's on the far right.
Oh, yes, he's on the very far right of the photo. If they could standardize on Miranda, he said no. He said you can make it look like Miranda, but if you're going to do something, it has to be visually distinct enough for the people to tell it wasn't Miranda. So they went off and they spent 3 years building a committee to define a language. So Haskell is a language that was designed by committee, and for such an enterprise, it seems to have turned out remarkably well. And one of the things that worked really well for that was the fact that they had a language to sort of base it on, Miranda. So whenever they couldn't agree on a thing, they just said, we'll do what Miranda did. So you had the benefit of a strong hand at the tiller even when it wasn't active, you know. But also they came in with a very experimental mindset. And so Wadler was very active. He co-authored the initial report, or co-edited. One of the things that came up along the way was that Joe Fazell had this idea that overloading, if we're going to allow some form of operator overloading, it should happen by talking about a type for a function that has some extra information that tells you about what overloading can happen within it. And Wadler misunderstood him, and we got type classes. So that is really where type classes came from, by accident. So how many people here are not familiar with type classes at all? Let me start there. Okay, so I've got 10%, 5%, something like that. So I'll go through this portion relatively quickly. So I mean, the main thing that type classes let you do is they let you add behavior to existing data types. When we describe the behavior of a class, we do it on an instance by instance basis. Okay, so here we're saying that there's a class for equality. Unlike Java, every object in this universe does not come with an inherent notion of, hey, we can compare these two things for equality and somehow give them hash codes.
Yeah, that's a good thing.
Yes. So we have the ability to control what notion of equality we're going to be working with, and we have the ability to say, well, you can't compare two functions for equality. We can actually talk about the lack of this property in a meaningful sense. That the lack of an instance actually tells us something as well. So we can define eq for, say, unit, where the unit type only has one inhabitant, or for booleans, or for ints and chars, or for pairs. In pairs, it starts to become interesting because now we're starting to say that if you can tell me how to define equality for A and equality for B, then I can give you equality for pairs. And we can do subclassing. So this does start to sound a bit like OOP. We start talking about subclasses. We can say that ORD is a subclass of equality. We can do comparison, which is stronger, that ordering is either equal, less than, or greater than. And we can do our instance for bool and the like. But type classes are not the classes that we have in object-oriented programming. If you start playing around with like C++ and you look underneath the scenes of like how do we implement operator or overloading of virtual functions inside of C++ or in Java or in these other, like, well, let's just look at C++. In C++, we have some notion of like a vtable where you point to where all the virtual functions inside of this object are defined. So if you go to invoke a function, we look in the vtable and we jump directly to that, to the function that's pointed in there. In type classes, though, we have cases where we don't have an object yet, but I'm going to give you a vtable. It's directed entirely by the type. It's not directed by the term itself. So here's num, and we can start talking about addition and multiplication and minus and negate and abs and signum, and we can put all of those into everything so far, up until that point of from integer, we could put into a normal object-oriented framework. Every single one of those things could be added as a member to some data type. So we can make a class that has a virtual function for how it's going to do addition between two things. It's going to be a little bit funny, though, because it's not quite clear. Like, if I want to add ints, I only want to be able to add ints to ints, perhaps. Maybe not ints to doubles. With C++, we wind up with sort of weird ad hoc coercion rules that let us move up and down a fixed class hierarchy, a fixed hierarchy of primitive types that we can go through and mash together. But here, we're saying something a little bit different. We're actually able to say, I want to add two things, but I can only add them if they're actually the same type. We're not coercing one type into the other. We're saying that the two types have to match, and then I can add them. But not only that, because the sort of vtable, the sort of dictionary that carries around all the methods that we're working with, is described entirely by the type, we can make a function like from integer. Give me an integer, and I will give you a value of this type A. Okay? And that has sort of very far-reaching effects on the design of the language. You move a little bit further along in the history of Haskell when you get to Mark P. Jones going off and building Gopher, where they invented constructor classes, which let us talk about things like monad, where we have a abstraction that we can now talk about where M is not even really a fully generated type. M of A is a thing that we can actually get our hands on. And to be able to define monads, like Gopher brought that to the table, and then I think it was brought into Haskell 1.3, somewhere in that, I don't remember the exact version of Haskell.
Yeah, 3 sounds, 1.3 sounds right.
Sorry, I'm not a Haskell historian. But it let us start talking about things that are very far removed from what you can talk about in object-oriented languages. Because how would you make an object with return? You could make an object that is the dictionary that describes how you're going to manipulate things. But to get there, we wind up having to do all sorts of crazy very non-OOP-like reasoning. So we can build our instance for monad, for list, or for IO, or for maybe, or for either. And then pretty much anything that has sort of this notion of embedding a value and sort of chaining operations with the right laws is a monad. But all is not well in the world. Yes?
Don't answer this if it would take you too far afield, but I suddenly realized I'm very vague on the question of if you don't have a V table associated with a class, what do you have underneath? Like, I call a function. It has to go find the definition of the function. What does it look for and when?
So what we do is we use the types to go through and resolve what instance you're looking for. So if you're looking for an instance for, let's say, eq of a pair of int and bool,
Okay.
right? Then what it's going to do is it's going to look at this eq of this instance down here, which says that if you need a pair, an instance of eq for a pair, then we need an instance of eq for the left-hand side and an instance of eq for the right-hand side. And then we know that we have an instance of eq for int, and we have an instance of eq for bool. So what we have is a series of rules. It's a logic programming style of dispatch based on the type information. We literally can pattern match our way through the type and figure out where we go to get the primitive building blocks to build up our dictionary.
So I can see that being much more powerful than just which has only one table for each.
And so what you wind up with is a case where the types actually change the meaning of your program, which is a very different sort of toolbox than if you were to come from, say, Scheme, where you can talk about all sorts of things that are sort of very V-table based about how you deal with overloading operations at runtime, or in C++ or Java, where all of those are sort of V-table based, where the V-table has to be bolted into the object. In Haskell, we separate those out, and the V-table gets plumbed around by the types, and then it's brought into use at the place where you go to need it. Was that what you were trying to get to? Or?
I was trying to check that the thing that the type is carrying is essentially the same kind of thing as a V table.
Yes. So from the type, we can derive, we can build up the dictionary that acts as our V table.
But it's all at compile time.
It's all at compile time. We figure out how to plumb these things through. And these basically become, if you have a method that takes eq a as an argument or num a as an argument, it's basically taking in the dictionary as an extra argument. But we're not giving you the ability to pass it explicitly. Okay, and that's going to be really the thing that's going to drive the next point home, which is that there are, we talked about OOP classes, we talked about num. There are lots of languages that have what Scala calls implicits, which are often billed as an improvement to the notion of type classes. And I want to talk a bit about the power you gain and what you lose as we go. Okay, so there's languages with type classes. Haskell, we have clean, which technically does have type classes. It has the coherence properties that we want.
For sure.
We have our little compiler for Ermine, which has type classes. I can't think of any others on the top of my head. I went to go make a list.
Does REST have that?
No, there are languages with implicits or type classes in scare quotes. But they actually don't have this coherence property that we were just talking about. We have traits down in Rust. And to my knowledge, you can actually pass explicitly properties of traits due to the way they handle orphans. I may be wrong on that, but my understanding from a big, long debate where they tried to drag me into the discussion on both sides was that traits can, because of the way they handle orphans, can be abused in the way that these things here can.
For a higher kind of type, is it easier or harder to get that from one or the other?
Well, when you want higher kind of types, Scala can talk about them, like Haskell can talk about them, in some sense. You have to just always talk about them with all their arguments applied to. There's no kind system per se, but
You'll see a big discussion in Rust on that. Some people want them, some people don't.
Yes.
But if they want them, how do you define it?
well, yeah, there's that, and there's all sorts of representational issues about Rust, polymorphic recursion issues in Rust. Rust is not a panacea. It's got many things going for it that I happen to like in terms of systems programming, and it seems to be the only serious player trying to tackle the sort of systems programming market. Even Go has sort of acknowledged that, yeah, we're not really a systems programming language. We have a garbage collector and stuff.
Yeah, just worried about the beta versus VHS where Go, because it's already been 5 years and they've got a head start and people are using that, and it's just sorry.
So the observation was is Go just because beta versus
Google-
VHS having come in first.
Google's bigger than Mozilla. They're going to win.
But I think really that Go has a different target audience than Rust. It came out of the gate going, hey, we're going to do system programming, but they seem to have backed off of that message. Yes.
Is this sort of accepted that you would put these languages in the same bucket like this, or
Is this sort of accepted that I would put these in the same bucket? Perhaps, I don't know. So Coq calls what it has type classes. But what I want to talk about is how the properties that it has act a lot more like what Scala calls implicits. Or Agda has what it calls type classes, but the properties that its type classes have act more like, now Coq and Agda have implicit arguments, which have nothing to do with Scala implicits. So perhaps the naming convention is terrible. There's just no name for the thing.
Agda calls them like instance arguments or something.
Yeah, instance arguments would be the Agda vocabulary. Okay, so instance arguments would be perhaps neutral vocabulary. I'll give an example here. I'm going to dip into Scala for a second. So we can define a class for semigroups. So we're going to make a dictionary that we're going to pass that holds on to how do I make a semigroup for A's? I have the ability to smash two values together and give back an answer, whatever the A is. So I might have a semigroup for int, and that is a binary operation on ints with an associativity law that's not checked, but we have it. And then a monoid is a refinement of a semigroup adding a unit. Okay. And we can start seeing a couple of benefits here, actually, from the Scala approach, which is that when I go to define a monoid, and I have a monoid being a subclass of semigroup, I can actually define the monoid all in one definition. This is actually a win for the Scala approach over the Haskell approach in terms of the amount of code you have to write to instantiate something deep down in the class hierarchy. So I could say that if I wanted to make a monoid for strings, I would use concatenation to add two strings together, and the unit would be the empty string. Or if I wanted to use a monoid for int, this one might be a little more contentious. In Haskell, we don't actually have a monoid instance for int. Because which monoid instance for int did we mean? There's actually several available to us. We could have addition. It seems to be the obvious one. But we might also have multiplication with 1 as a unit. We can also have min with the maximum bound of ints as a unit. We can have max with the minimum bound. Which one of those did we mean? There are several monoids to choose from. And so here we can go through and define, given a list of values and type in A, we can take an implicit argument that is our monoid, that is however we want to manipulate our list of values, and we smash them together. And so we can go through and sum lists or sum strings. And we gain power here. we've gained the power that implicits can be passed explicitly. If I wanted to make a new monoid that's also a monoid for int, I could make the product monoid. And now I could choose to call sum with the sum monoid or with the product monoid. So we won. So I'm going to turn to a functional programming stage. Powerful you have become. We have the dark side. I'm gonna turn to Yoda for many quotes as we go. So to kind of see where this goes wrong, I want to talk a little bit about why functional programming is productive. Why people seem to get mileage out of writing things in Scala versus, say, Java, and find that, hey, look, I was able to get away with a factor of 20 less code, and I was able to express the same idea. Why did we win? You know, why is Haskell so much more expressive in the amount of code that we write than other languages? And I think the flagship reason for why functional programmers win on so many fronts is that we get to use really dumb reusable data types. We get to make a data type for pair and use it forever. And we're willing to do that. Like, it's not an enterprise Boolean that we've actually seen in production where, you know, you've got some like Java Bean crazy framework, you know, and you have to have your Sun certified enterprise architect hat on in order to understand all of the machinery. But in the end, it's just a Boolean that indicates whether or not a flag is set, right? We just reuse bool. We have the type. We give it a name, and we can work with it. Or if we need to talk about a value that might not be there, we put it in a maybe rather than deal with null, right? Because otherwise, you wind up running into the classic scheme problem of you have a container like an association, an A-list of some sort, and you want to go see if a thing is in there. Well, did you pull out a null, or was it that it wasn't in the list? You need the wrapper that tells you whether or not you got a thing, right? So being able to have a container that can hold a value that happens to be null requires some kind of like give and take on the vocabulary. You can have multiple layers of maybe. You can only have one null. So we get a lot of mileage out of this sort of dumb reusable data types. But we have a habit we do in Haskell that I'm going to actually do a little bit of coding on the fly here. Hopefully this will get rid of Yoda here. So when people come to Haskell, one of the first things they try to do, let me see if I can make this large enough for people to see, is they go to say, well, I want to make a data type of like a vector, and I want to hold A's in it. But I really want to be able to say that the only A's you should be able to put inside of your vector, I'll say this is a two-dimensional vector, are numbers. Right? If it's not a number, you shouldn't be able to put it in here. But this comes at a real cost. Once you say that, you've ruled out all sorts of standard classes that we could have previously made instances of for V2. So what we might want to say is that if you want to have a num for V2 of A, we just need to know that you have a num for the A's themselves. Plus V2, CD is V2 of A plus C, B plus D, right? We could go on and implement the rest of the methods. But what we've done is we've moved the constraint down to where it's used and taken it away from here. The other thing is to note is that this place of putting them is something we had called data type context. It didn't actually give you the ability to get that fact out of the object that you built. You could build like data v2a where using GADT syntax, and you could put a num a dictionary in here, and you could say, give me 2 A's and I'll give you a v2 of A's. And now I could actually, for the most part, get rid of this, but I can't because from integer it's going to need it, because I'm going to need to construct one out of the whole cloud yet. Mm-hmm. So I haven't really won anything by carrying around this dictionary here. But what I've cost myself is, now how do I go through and do fractional or other instances that I have lying around? If I need more from A, in order to say something more about V2, I'd have to make a smarter V2. I'd have to make a V2 that carried around, well, what type of number is it that I'm working with? Is it a number that's fractional and floating and has all these other properties? Does it have eq? Does it have ord? I mean, we may or may not have those properties and still have a num. So you start winding up with the sort of the entire lattice of possible properties that we might want to have to worry about if we baked it into the dumb data type, or into the data type. If our data types cease to be as dumb as they are and started to know more about the values that they hold, then we wind up with this profusion of different data types, and it destroys code reuse. So one of the things that really kind of drives me to write Haskell is that I've actually been able to achieve the thing that I thought I was actually getting I was trying to get my entire career writing object-oriented programming, which is I'm actually able to get code reuse out of my code. I'm actually able to write code and sit it on top of other code that I've written before and not have to go back and rewrite everything because I wrote it at the wrong level of abstraction. And the tools that I have that seem to get me there are parametricity, the ability to reason about free theorems, the fact that I have very dumb data types, and the ability to refactor code. So I want to talk a bit about some of those points as we go. So I should be able to pick this up from here. All right. So here we can have a dumb data type composition. So functor composition, well, it may be functor composition. It's just compose f, g, a. It's the f of g of a. So if we have if f and g are both functors, then the composition of them is a functor. If they're both foldables, if we can go through and get a list of values out of them, I can get a list of values and I can flatten that down to get a list of values. So I can fold through the composition of two things. If I know how to traverse with special effects, I can do that. It turns out that they're applicative, and I have a typo there, it should be an applicative G. Then the composition of two functors that are applicative is an applicative functor. Unfortunately, it doesn't work out the composition of monads. But we get this sort of laundry list worth of properties. And then knowing a little bit more about my individual elements tells me more about the composition. It lets us reuse the same dumb data types over and over again. And we can reuse the same combinators over and over again by putting just enough constraints on the combinators to actually be able to use them in the largest number of possible situations. So we move the constraints out of the data types and into our functions. Like, this is the thing that trips up newcomers to Haskell all the time. They want to be able to make a data type and they want to have it hold on to all the facts that they know about. Every argument I have is going to ever be a number. And we had data type contacts through, I think Haskell 2010 killed them.
Yeah.
So it should be 2010. And that was that sort of num-a constraint. But it didn't actually give you access to a dictionary of num-a. It just said in order to call the constructor for this, you better have one of these instances lying around or it won't let you do it. It didn't actually give it to you later, so you got no power out of it. All it did was tie your hands. And for a while they were used on complex numbers. I think it used to be a constraint that said you had to have real float. If it's not a real float, you can't make a complex of something. But that meant that complex could never be a functor, it couldn't be lots of things. And those functor, foldable, et cetera, reversible instances, those are actually quite useful for various operations. It'd be really nice if you had a complex float and you wanted to convert it into a complex double to be able to just say, could you please fmap, real to frac over this. And real to frac lets you convert between two different fractional number types. So that's dead because of the use of data type contacts. So that's why we ripped them out of the language. They're just not around anymore. They were originally put in because of strictness annotations and seek.
I don't know why they were put in.
Well, my understanding was because of seek.
I think they predate that.
Do they? Okay.
Yeah. It doesn't make any sense why they would exist. But
All right, so Dan doesn't know why they exist. I don't know either. So we'll appeal to Yoda again. And I think the key insight here is that the correctness of moving the constraint from the data type to the use site is actually predicated on one of those properties that we had in type classes that isn't there in implicits. And that is that it doesn't matter where I get a dictionary from for a given type. It's always the same dictionary. So if you give me an eq int, it will always be the same equality. You can't make a local definition that disagrees with it. No matter where you get that eq for int or list of int, it's going to be the same dictionary. Now, we technically have some incoherent instance nonsense that some folks can set up, but it might as well not exist. Yes?
What do you mean by where you get it from?
It means that if we look at implicits, when you call the function that you've defined here, when you call some, you might have different implicits in local lexical in scope that are available to you. And in Scala, it uses some ad hoc rules to go through and figure out which scopes are closer to you, and then takes the one that's closest under some arcane structure of close. What's the best instance for a given to pass for a given implicit argument? Okay, and the rules are actually quite complicated. I can't give them off the top of my head. In Haskell, if I'm looking for a monoid for int, there's only one in your entire program. Now, GHC doesn't technically implement Haskell correctly in that sense, and there's a few places where you can actually see the fact that GHC's sort of mechanism for implementing the abstraction that we have is not quite up to snuff. But there can be one monoid instance for int for your entire program, basically.
The Platonic ideal of Haskell.
Yes. In the Platonic ideal of Haskell, Haskell as per the report, not Haskell as per GHC's implementation.
There's a Platonic ideal.
When you say in your whole program, does Haskell have a concept of compilation units? Like, what is a whole program?
So that's part of the problem here is that what you need is the fact that you can't make you shouldn't be able to make an orphan instance for, say, eco, or say monoid for int in some module, and then it's elsewhere inside of your program make an instance of monoid for int for the same, for monoid for the same type in different modules that don't have a dependent relationship on each other. GHC, on the other hand, doesn't actually check that. So there's some situations where you can have a data type defined someplace and a class defined elsewhere, and then two modules that depend on both of those things, and then make up local instances that happen to be orphans because they're not defined with the data type or with the class.
Okay.
And then have yet another module that depends on both of those, and then have problems.
Okay. So when you said there were loopholes, the loopholes do have to do with separate compilation?
The loopholes are brought about by separate compilation and not having a global consistency check after the fact. So they are largely systemic and really do need a sort of global check on the program. Yeah.
What happens?
What happens is you can lie to yourself, and you can make everything I'm going to say for the rest of the talk a lie.
It will compile and then it will pick one of them?
What will happen is the one that's in local lexical scope will be the one that you get. So you would start caring about the provenance of where you got the instance from.
Okay.
And pretty much the rest of my talk is going to be talking about the sort of Platonic ideal of what type classes mean, why that's a bad thing. Or at least, sort of why that, for me, that's turned out to be a bad thing. Because with implicits, we have power to pass whatever instance we want. But now, I now have to care, if I have an argument that's monoid int, did it take the one that I passed it, or did it take one that was in ambient scope? I have to now know how that instance got to me. It becomes another concern, another ball I have to keep up in the air and keep juggling. Okay. And this matters because we like having dumb data types. In Haskell, we can have, for instance, a set data type for a set of A. And that set is built as a tree of bounded balance using the ordering on your A's. But we don't have the set construction taking the dictionary for int, or the dictionary for A, for ord A. But we have the individual insert and lookup operations taking the ordering on A. In a world where you had implicits, you could pass the wrong ordering at different times. You could pass one order that sorted things one way and one order that sorted another way when you want to look things up. And now you start having spontaneous failures of lookup based on what instances were in scope at the time you went to go do the operation. And the cost of this is that now you have to put together some kind of social contract that says, don't do that. And then you always have to worry that somebody did that. It's a perpetual source of risk. throughout your reasoning process.
So
Yes?
why isn't that a case that at least in that instance, the order should be associated with the set rather than its function?
That is a reasonable option in the case of sets. Set is one of those cases where you could actually make a reasonable case that you'd want to bury the ORed instance inside of the set. We'll talk a little bit later about some algorithms that makes it possible. So that's a thing we're going to address fairly late on.
If you're unioning two sets, that kind of
Yeah. So it turns out that like if you do that, if you say that I have an ordering instance on and I've buried it in my set, then if I go to union two sets, the only thing I could do is I would ideally be able to say, let me take, let's just, like the simplest thing you might try to do is take which one of the two is smaller and insert all the elements of that into the other one, element-wise. Because I don't know anything about the dictionary, so I don't even know that they have the same ordering.
Well, wouldn't you then wish that the type of union could assert what the orders and that the
That is a perfectly reasonable stab at this problem, and we'll run into problems with it later. So I have a slide that talks about why can't you just, and then I give like 6 items, and this is one of the items in the list. So why don't we punt this until we get there, and then we'll come back to it. Because there's unfortunate, there's a hole in that bucket, dear Liza, dear Liza. By the time you get done to it, you can't, you kind of tie yourself in knots. And we'll deal with that in a bit. I apologize for punting on you, but.
By the way, this slide shows where you can get multiple dictionaries for a type.
Where at?
That one. You can get a num A out of the GADT.
Oh yeah, here we can get the num A out of GADT. I was just all I was showing here were just different notions of data type context. I was going to talk a bit about that. That was kind of a data type context versus GADTs versus just having a dumb data type that has no dictionary. Here, you had to use the dictionary in order to build the thing, but you didn't get any benefits. With GADTs, you can carry around the dictionary and you can get it out later. But now, if you need something that's stronger than num, you would have to make a completely different data type to carry around this stronger property.
Okay, but if you have a v2 of int, now you can have 2 num ints in scope.
Yes, but they would be the same, yeah.
With type classes, you know they're the same.
Yeah, with type classes, you know that they're the same. Whether you opened up a GADT and you happen to get a thing out, or you just took the num int that happened to be in ambient lexical scope. In Scala, you basically have to use these arcane rules that are going to say, well, you opened up this thing and it's the most recent thing you saw, so this is the one that you get. And you have to keep those rules in your head. So, data type context. And for me, I think the real key is that this is for me, a refactoring tool. I can take code that I wrote, and I don't really care too much about what the instance structure that I have lying around is. It will plumb all the stuff for me to the place where it needs to be. And I don't care if I move the constraint into a method, if I carry it around in my data type. They're both going to give me the same answer, because it doesn't matter if I had the GADT that was carrying around my num instance for me, or that I had some weird data type context that required you to prove to me that you have a num instance for the A's when you go to build the record, but didn't give you actually any benefit from that fact. All of these things are going to be working with the same num int in the end. And that's a pretty big, powerful tool for me. The fact that as I refactor code, I'm not worried about those concerns is, I like to keep a lot of plates spinning up in the air, and it's just a whole set of them that I don't have to even worry about. They're handled for me. And it's really, we don't know what we're going to do with the code in the end. So turning around and making things as generally useful as possible, like making a data type that can be used in the most number of situations by dint of not carrying around this dictionary, not carrying around the tag so that Union can see it and then know that the two sets are actually built with the same ordering, which is effectively carrying around a type so that we can dispatch the vtable later is saying. And so ML modules give us a way of sort of making like global selections of a property. I want to take this chunk of code and parameterize this on, this entire chunk of code is going to care about some random number generator. It would be really nice for me to just say, and use this random number generator. In Haskell, like to work with type classes, you could add a parameter to every data type, every function call, pass proxies everywhere, and then somehow use that type to figure out what random number generator you're going to work with. It would be a global refactoring on the program that you have. And so in that sense, I would kill to have ML module like tools available to me in Haskell. The ability to say, I want to parameterize this entire module on another module that provides me a random number generator. So I could sort of factor out, currying out the arguments that I want to have everything in tier agree on. That would be great. So in that sense, I really like ML modules. I think that they're a wonderful tool. But they're not type classes. Type classes will do that, well, figure out the instance for me thing in a very clean way. It will pick and do the plumbing to get the dictionary in the right place. With ML modules, I can build a functor that will take another module and I can plumb it around and I can open it up manually in the local context where I want to work with it. And I can access foo dot some property out of that module or open it or deal with it locally. But I have to be very explicit about this. And to be honest, that plumbing is something that I really don't want to care about. The power of type classes is that the types are enough to direct this information for you. And 95% of the time, that is perfect and you don't even need, there's no new type noise, there's nothing getting in the way. It's that 5% where you have to like use the const type or identity or something like that, where you're putting on and taking off new types just to inform the type system that people get really upset about. And then they say, well, if I had ML modules, that 5% would be awesome. The problem is that you pay for it the other 95% of the time. So again, ML modules are awesome, but I think they're different. They overlap a lot with the use cases of data types, yes.
Would you put Scala in the same bucket?
Well, Scala modules, basically where you build an object and you use it like a module, fits in the same, you get the same power benefit ratio. It just happens to be that they just build it out of objects.
They're not quite as good.
Yeah, they're not quite as good. There's a few things that you can say. Well, there's a number of things you can say with modules that we should take offline, but.
Is there any reason ML modules and type classes couldn't coexist?
Not really. There's been a lot of work in this space. Manuel Chakravarty did a paper at one point in time showing how to encode one as the other, and vice versa, to show that they're sort of equivalent in overall expressive power, but not necessarily in terms of the amount of code that you have to change when you change something. There's currently some work going on. Scott Kilpatrick and Edward Yang have been spending an awful lot of time working on something called Backpack, which tries to bring a sort of module-like system to Haskell, where the modules aren't the individual modules within a package, but they're the actual packages themselves, sort of the grouping of modules become the things that become parameterized in other packages. So there's work pushing forward in that space. But it turns out that the instance infection, sort of the mechanism by which we sort of bring in all the instances that came in with another, that were in scope from everything that you used as those infect your interfaces, causes all sorts of problems with deconstructing modules in the first place. So there turns out to be problems around these orphan instances where you can say, I have an instance that I want to define for a data type that I never made up and for a class that I didn't make up. I really want a monoid for int, but I didn't define monoid and I didn't define int. So I could make up an orphan instance in my own code, but that orphan instance is fundamentally anti-modular from the standpoint of trying to bolt in like an ML module system. So there's been a number of issues around that have come up. Yes?
Sort of an aside, but I've wished for a long time that there was some mechanism in Haskell to allow a big system that uses like multiple different versions of the same package in different parts, even if the parts never talk to each other.
So there's the issue of trying to allow multiple versions of the same package in different parts. That's actually a thing that's been
an instance of the same kind of thing.
Yes, it's a related issue. And there's been a lot of work within, I don't think Hood cares an awful lot about this problem, about having private dependencies. Like, if I use parsec internally I use parsec too, but I never expose any one of parsec's types to my public API. Why do you care that I used an old version of parsec? That should be a thing that we should be able to encapsulate and keep local and private. And that's an infrastructure tooling problem that we just need to tackle as a community and figure out how to talk about those things. So I agree. That is the same sort of thing.
That seems to be critical for being able to write systems beyond the given size.
Yeah, now the thing is if it owned its own data types and had its own classes, then the instances that it would have would be instances for its version of the thing. And that actually works out okay because you would have, if you look at the sort of like typable, the actual package and version and all that kind of stuff falls into the type of everything. So when you go to compare types for quality, that's all done off of that. So here I want to talk a little bit more about constraints and one of that sort of uniqueness property that I've been beating up on so much that makes type classes so well able to be reasoned about. So as of, what was it, 7.4 we first got constraint kinds? It's a terrible name for the feature. They call it constraint kinds. There's only one constraint kind. I don't know why the extension is named constraint kinds. It's constraint types, really. So what we gained in as of 7.4 was that there's now a kind named constraint. And this lets us actually talk about eq as a type that has a given kind. In this case, eq is a type of kind star to constraint. Eq says, you give me any type of kind star, the thing that has values like int is kind star. Then eq int is a constraint. So the stuff that goes on the sort of left-hand side of that double arrow is of kind constraint. Eq, ord, show all take stars and give you back constraints. Monad is funny because it takes star to star to constraint. It's parameterized on something of kind star to star. Now, something that's near and dear to my heart, a little bit of category theory. I have to terrify everybody every session here, or some people every session, is that I could go through and I can define a category turn on the language constraint kinds, worst name exception ever. And now we have the sort of standard definition of a category that comes with GHC, which is that the identity function is that, and if you want to build composition of two functions is the obvious thing for function composition, but we can actually build a category worth of constraints. It talks about entailment. This constraint entails that constraint. Yes?
Okay, waited too long to ask. So you said you added constraint to the language. What did that do? Is it just
What it
name
let us
something?
talk about is it lets us talk about variables that have kind constraint. So I could define like a data type dictionary of P.
So make constraint like first class, like you would say in scheme.
Yeah.
Becomes a first class object.
Right? So before, what I could do is I could have written ord dict of P where, let's do ord dict of A. Right? This would hold on to a dictionary for an ordering for some A. And then whenever I pattern matched on this instance would come into scope. It would tell me, here's a proof that there's an ord instance lying around for A. Like when we wrote that data v2a, where v2, here's a proof that A is an instance of num. When I pattern match on v2, this num instance comes into scope, and I have a local proof. Even if my function didn't have access to that proof by other means, it would now have access to this v table, this dictionary that passes around the fact that A is an instance of num. Here we could say it for ord, here. Here we can say it for any constraint. And we couldn't say that until we could talk about eq itself as a type. Right? So here, P takes anything of kind constraint. So we can talk now about a dictionary for eq of A. So like a dictionary for eq A, this would type check. Dict is can be given the type dict of eq of int, and I could pass this around, call a function with it. You could open up the dictionary and get out your eq of int, your proof of eq int. You'd get out the v table.
Sounds an awful lot like the implicit arguments thing that you just said you don't like.
But we're going to talk about some properties that make this never bad. Okay? So now we can go through and we can make a new arrow type, kind of like our, we can say that P entails Q says that if you know how to give me a P, if this says, if you can give me a P, a proof of P, then I can give you a dictionary for Q.
Sub?
Yeah, it's just the name of the constructor for this. I just needed to make up something.
Why do you call it sub?
It's
Call it
sub.
nibble.
I use sub in the constraints package, so this is like it's ingrained in my brain. So now what we can do is we go to define an instance of category for entailment. Now id here says, what is this? This is going to be KAA. So given A, I should be able to give you a dict of A. Well, that's just dict. That's exactly what dict says it can do. So I can pass this thing, dict, as the argument, and it will take whatever constraint A you give me and just wrap it up in a dictionary and give it to you. But composition is really freaking hard. I don't know how to write it directly. I do know how to write a combinator for it. I can write a little helper that says that if you know P, and P entails Q, and Q entails some R fact that I'm interested in, actually, and Q entails R, let's do it this way, then R. Okay, so here, this is kind of funny because we're not used to seeing these things sort of naked in negative position and stuff like that. This is actually an argument that says that if you can give me a Q, I can give you R. Then what I could do is I could just say Q to R, and then the right-hand argument is something. I'll just do this. All right, so how does this work? In order to discharge this obligation, I open up sub. Now sub gives me a thing that says that if I knew P, I could give you Q. But I know P, so I can discharge the obligation on P, which enables me to pattern match and get to dict, which takes the, which was the dictionary for Q that we got out of here. And when we're done, we've now proven Q, so this argument can be patched. Like GHG is doing all of this behind your back. It's plumbing all of these things for you. Yes?
Should there be parens around subdict?
No, actually. The precedence rules application binds tighter than everything else, so it doesn't matter. I try not to use unnecessary parentheses. So. Yeah. So no. And then when we're done, here's the R that you requested because we've discharged the Q that we needed in order to get it. Okay? So this lets us then like define composition. P and Q is, I think, sub of dict of...
Double backslash. What's that mean?
Just like substitution by...
Oh, is that a symbol you just created?
Yeah, I just made up a symbol. I made up an operator.
That's awesome.
And so you might have to set the fixity on this, but this would be how you would define composition. If you work through what this is doing, I'm changing the type of dictionary, changing the type of the dictionary through the subsequent applications of these things. And in the end, it gives me the composition that I want. Yes?
I'm still stuck on the use of the equal arrow with, on the left-hand side, the
Here?
type without a type class in front of it, or like just P.
P arrow.
Colon P without
Yeah, almost everybody's, like, people have intuition for this. But we can make variables that bind to the whole constraint itself. And now you can make, before we could make or dict of A, and we can make eq dict of A, but now we can just talk about dict of eq of A, or dict of ord of A, or dict of show of A. And I was able to write one data type and reuse it, right? It's that dumb data type that I can use in many different situations. The thing that I like about functional programming. Having a kind, having the ability to talk about eq in isolation without having eq applied to a thing lets us talk about this sort of.
Would you mind changing the name of either your dict data or type constructor so that those of us who are learning this can tell them apart?
This has to be dict d. So d, something like that.
You should probably put parens for the double backslash use.
Yeah.
Not everyone knows what the default is.
That was a useful suggestion.
All right. So by the time we get done with it, this should be able to compile, I believe, if I.
So when was that added?
What?
That feature was just added recently?
Well, the constraint kinds? 7.4 would have been, what, 3 years ago?
I don't know, I guess.
Somewhere around there. About 3 years ago is when we got.
You're going to need G82s before you.
Yeah, I need G80Ts and all sorts of things here.
Does this run on LLVM or is this the GC or is it?
We have LLVM backends for GHC now. In general, we by default compile through our own native code generator.
I mean, how's the performance of this? I'm just curious about.
It's ridiculously fast. It's not. That is not a. This is not a. This is not anywhere near our performance model.
I mean, why would I just? Oh, I don't know, like I said, the more I look at this, it's just like getting closer to the math. It's amazing.
I need type operators. Let's start doing the dance.
I'm seeing parallels, like.
It's a GHC prim for constraint?
Maybe.
You know, just started looking at Rust. I see similarities.
Yeah, yeah.
Language, types. All right, woohoo! So now I should be able to say D has type dict of eq int. I should.
Oh.
Why do you have to turn?
Let me make an instance of show for this.
Dict P.
Show string.
It's not going to work.
What did I screw up?
What?
He,
Oh, dict P.
no, Dict P.
Yay! That's proof that int is an instance of eq. Nope. All right. Right. That's a way of checking, like that I was able to discharge this obligation, that I could make the instance of eq in order to prove this. Yes.
You keep talking about discharging proof obligations. Is that translatable into the idea of being able to find the v table for this function?
That's basically what it is. The v table itself is a witness, right? We have programs are propositions, or sorry, types are propositions and programs are proofs of a proposition, right? In this category of constraints, that's actually far more accurate. We have propositions and we have proofs, and we don't. And it turns out that we're irrelevant. The proof itself must be irrelevant. I don't care how you get from here to there. In the absence of incoherent instances, all paths are the same. So what we can, let's see what that means. So I can talk about subdict. Give me a proof that ord of A entails ord of list of A.
Can I ask
Wait,
a simpler
can we-
question before
Yes.
we get?
Go ahead.
Is there a code transformation that makes the dictionaries explicit?
Well, by the time it comes out as core, it becomes explicit.
Well, but is it something that one can do on a small scale by hand to demonstrate what's going on?
Ooh.
Can I ask an even simpler question?
I'll take the simpler question, yes.
Isn't show string the identity? I'm very disturbed by that show string.
No, because it goes out as show s, which is actually a difference list of string to string. It's a string to string. I could have written this as show for D is this. But then if I had like something with arguments and I wanted it to put parentheses in if it was used at a given precedence, so by default, my way of writing show is always to write the correct, the thing that will be correct no matter how complicated the thing gets. So I use show string for that.
Can I rewind? You said vtables are witnesses, but you didn't finish the sentence.
So vtables are a proof that an instance is available for a
Because
given.
you can actually get the table,
Yes.
so that's.
It's a proof of, like, a constraint is like, a constraint is a proposition, and a vtable, or dict, is a proof of that proposition. A dictionary or a vtable would be a proof of that
And
proposition.
earlier you were talking about how in the Platonic ideal case, there's only ever one proof of this proposition.
Well, what I'm going to say is that you can't distinguish between the proofs. That's the idea. And that's going to be the thing in the ideal world, yes.
The useful thing is that there's some information you can extract out of this proof, which is how to actually do the methods.
Yes, I can get from here to there. Given this constraint, I can get to that constraint, yes.
So I've never seen constraint times before, and I think I kind of get it, although I didn't really follow the details, but I'm more concerned that I lost what the connection was to the main argument you're making in the talk.
So let's go back to that. And that's the point here I wanted to show was a couple of things, and then I'll be able to. I have a slide that will pick up from here.
You'll pop.
Yeah, I'll pop back to a slide.
Updated table.
So I should be able to set minus x.
That colon dash, what does that do?
That's just that's a name that I made up for the
Oh, keep doing it.
subject. Oh, did I? Sub D.
You can
So
make
you
up your own
promised
operator.
us that we go deep into category theory, but you will pop back to the dumb data types and composabilities.
Yes.
But
Practical engineering.
everybody keeps solving these problems. Wouldn't you just write all these, put them in the library, just use it? That.
He wrote the
I
library.
wrote the library. I'm explaining how the library works.
No. So all this stuff already exists for Haskell. You can go load.
You can all install constraints, and it just does this. All right. So here's a proof that if you know how to get an ordering on A's, I can give you an ordering on a list of A's, or a list of A's. I'm asking GHC's type checking mechanism to do all the work to figure out how to plumb this for me. It just built the whole proof that from here I can get to there. Okay, and I can do, like, I can go from ord of A to eq of list of A. Now, how can I do that? Well, we know a couple of things about ord and eq. Okay, so let's walk through the properties that we know about them.
You sure one that doesn't work?
Yeah, sure. Ord A entails eq of B. Can't deduce eq of B arising from the context ord of A. I don't know enough to figure it out, right?
How about eq of int?
It's pretty snappy.
Ed,
That we know.
once you're this far into constraint magic, can my hypothetical whole program Haskell compiler still erase them all?
Can your whole program optimizing Haskell compiler erase them all? No, because it can never erase. It can never erase them all because we have things like polymorphic recursion, where you're building up dictionaries for finger trees and things like that, where you're building up dictionaries for based on lists.
It
can erase them as much as it can.
Yeah, you can erase as much of this as you possibly can through some super optimizer or something. But you can provably not do it for everything.
One of the nice things about type classes in the raw is that you can at least say that if someone made Milton for Haskell, the dictionaries wouldn't be around.
Yes. If you had language that was as crippled as would be necessary for that. So here we can say, like, you can give me an instance for ord A. You can give me an instance that, I don't know, A is, or int, you give me a proof that int is bool or something like that. And I can give you, that's actually going to get rejected by the type checker before it gets there. But
What, open close? Open close?
Yeah, given any constraint, given the unit constraint, we have this. So we actually have a terminal object in the category of constraints because I don't care what you tell me. I can give you the unit constraint. We have xfal. So if you can prove that int is bool, then I can give you any constraint you like. I have an initial object, a terminal object. I have all sorts of nice category theoretic mumbo jumbo we can talk about here. Dict itself is a functor. It goes between the category of constraints and the category of Haskell data types. It's a fully faithful functor. Every function that you can go from dict of A to dict of B can be turned into, can turn back into an entailment that A entails B. You can go you can say all sorts of crazy things about this relationship from a category theoretic perspective. But one of the most interesting properties that we have is that this category is what's called a thin category. And this means that it's very well behaved. Given any two objects in this category, there's at most one arrow between them.
That's only true if the programmer is nice enough, right?
Only if incoherent instances die in a fire, yes. So if you pretend that incoherent instances were a bad idea and were never introduced to the language, then yes, it holds.
Yeah. Also,
So that's proof irrelevant.
Ord has to sort of agree with EQ in certain ways.
However, it doesn't matter what you write down for the definition. The user, without using incoherent instances, can't break this guarantee. So let's look at why. Okay, how would I get from ord of A to eq of list of A? Okay, I have two different paths. I could use the fact that I have an instance for ord that says ord of A and gives us ord of list of A. And so I could go down from ord of A to ord of list of A. And then I could use the fact that ord has eq as a superclass to forget that I have a full ord and just remember that I have an eq. Or I could use the eq entails ord, the superclass relationship, to just go from ord of A to eq of A. And then I could use the instance that eq of A entails eq of list of A to get down here. Now it turns out that the property that makes all of this nice is that this has to be compatible with this. You can't actually write code where that doesn't hold. Because otherwise you would have to have two incoherent instances that apply at the same type signature. Basically we can pattern match our way through the type. And that pattern match has to be uniquely determined, unless you have incoherent instances causing you problems. Yes. Sorry.
This is a theorem for free.
This is I don't think it's a theorem for free, but it is a theorem for really, really cheap based on the properties that we have. Yes?
So by compatible, you mean that the equality method that you get by forgetting the rest of ord agrees with eq, rather than the fact that compare of objects that register as equal.
That compare and the equal might disagree. That's a law. That's a thing that would be great to have dependent types to talk about. But it's not a property that we actually, that one is not what I'm talking about. What I'm talking about is that I don't care which, each of these paths through here would get me the same starting compare and get me the same ending equality instance on the list. This equality is not defined in terms of compare unless the particular instance was defined that way. And it would be compared element-wise. So what we get is this sort of lovely property that says, I don't actually care what path you take through this. And so every edge here is an entailment. This is ord A entails ord of list of A. This is ord of A entails ord of list of A entails eq of list of A. It's a category. I can compose these. And the nice property is that every ord of A entails eq of list of A is in some sense equivalent. The dictionary that I get out, given the dictionary I put in, is going to be the same. And that's a remarkable property. Because for me it means that I don't care if I pull the dictionary out of a GADT that you gave me, or if that I have it from ambient scope. They're going to be the same dictionary. If I got to the same conclusion, then this eq of A must be the same. Eq of list of A must be the same. So I think really this kind of shows that we got the power that we had from implicits by giving up something, right? Whenever you gain on one front, you usually lose something. You lose the ability to reason about something or whatnot. Here what we gave up was this sort of global coherence property that I think really, for me, is a big part of like how I can reason about Haskell. And really this coherence implies that however you refactor your code, it never changes the meaning. It doesn't matter what instances are in scope. If you had your set and you baked the ord into the set, or if you baked the ord into the lookup and insert operations, you will always get the same operation, or the same answers. In a language like Scala, on the other hand, where we don't have that property, that you could pass me a different dictionary for the same type in 2 different places. Now that's, again, it's power. We gained something. We gained flexibility in that sense. But once you can care about the provenance of your dictionaries, you have to care about the provenance. It's another plate you have to keep spinning in the air. It's another concern that you always have to worry about. Where did this thing come from? Which one do I mean? And one of the things that I like about Haskell is that I can put down that stuff because it's really boring. And this kind of points to the case where I was talking about earlier about sort of better algorithms. We can talk about hedge unions as an example of a thing. It's the class, like every time this comes up, this is the example everybody trots on. Oh look, but you can't do hedge unions using the Scala thing. And there's a huge element of truth to it. And I think it's a bad example in some sense because it steers you to believe that you could just make a tag on your set. You can make set XA, where X is some tag that tells us which equality or which ordering we really meant. Right? Like, when you only have one constraint that you're worried about, ORD, that's a pretty reasonable sale. Like, I could make that sale, and I can implement that code in Coq and Agda, and I can prove all the things that I need to prove about it. Okay? But we have a problem. If I flip back, I really should have put this slide in line there. To compose. Where do I put the tag for functor? And for foldable? And for the traversable instance? And for the applicative instance? I have 4 different tags now that I want, that may or may not exist. How do I track all of this meta information in one attribute, one thing, or one piece of information? And now if I wanted to sort of swap out F for G, I would have to make a combinator that knew how to swap out the old tag for the new tag that's now appropriate. I would lose the ability to use a general purpose combinator to refactor this. If we had a sufficiently nice notion of category theory, composition is actually a bifunctor. We can actually swap out these 2 arguments and do all sorts of things directly on them. You give me a natural transformation from G to H, and I can give you F of G of A, compose FG, a natural transformation that gives you compose FH, and stuff like that. I can map out under each of those properties. That's just gone with the sort of tagging model. And it's a fairly standard attempt at resolving this. And it's the one that I hear most often out of folks from the sort of Coq and Agda community as they attempt to try and recover this through the power of dependent types. They have type classes, but the type classes that they have are the implicit style, where I can pass in an instance argument whenever I want, as long as it carries around all the proof terms, whatever I have inside of it. But I don't have any sort of coherence guarantee that the 2 things that I have are the same. And that's actually kind of problematic. So if we go back to our ORD A, ORD list A, EK A, EK list A thing, here we actually don't get the guarantee out of, say, Coq's implementation of type classes. With type classes in Coq, what you can do is you can say that there is a path that we will take. This is the blessed path. You can put like a weird scoring system in, and it will say that this is how we will get from ORD A to EK of list of A. Damn it. Okay? Now, if you have an EK of A, you'll get to here, but I can tell you nothing about what that thing is. I get no proof that this diagram commutes out of the type class mechanism that we have in Coq and the equivalent mechanism that we have in Agda. There isn't an analog in any of these languages. And it's troubling to me that in the world of dependent types, that they can say all these things about everything else, but there isn't a dependently typed language where I can actually express the thing that makes Haskell go, this sort of global property about the language as a whole. So when people ask me, is Idris the future, is Agda the future, is Coq, the future circa whenever, I tend to shy away from it because one of the biggest tools that I have for reasoning about the correctness of my code is just gone. And I don't know how to really, jive the hey, dependent types are more powerful, go dependent types message with the hey, the tool that I have that makes it possible for me to refactor code without breaking it is robbed from me. So the hedge union example is something where we can start trying to, I think I have a, but why can't we slide? So one of the common excuses is, well, maybe you could just compare the two dictionaries to see if they're the same dictionary, and then you can do the fast, efficient hedge union, where you go through and, yes?
Stupid question. What's hedge union?
Okay, so let's say that you have two sets, that they're sorted by the same ordering. A hedge union lets me kind of walk down the two sets simultaneously and sort of graph in one into the other wherever I can say that this one completely surrounds the set of leaves that I have on the other side. So it sort of lets me divide both of my sets and insert grafting in pieces to build the new set for a hedge union or a hedge intersection.
The fact that it's hedge is super important here, right? It's just that the fact that it's hedge is not.
The fact that they both sets are built with the same ordering is what matters.
Well,
to make
but
that.
the point is it's a merge. The fact
Yes.
that it's hedge because you've got constant.
Well, the sort of the problem is that
If your sets were lists rather than trees, this would be the merge of merge sort?
this would basically be the merge of a merge sort. The reason I'm using this one, I keep trotting out this example, is because the naive solution that you have left to you, if you don't have hedge sort, is to insert the smaller into the larger, right? But that doesn't even work. Because now the dictionary that I would be carrying, the ordering, the choice of ordering, would depend on which set was larger. Right? The new set is really ad hocly specified at that point in time. So you'd have to say, well, I'm going to insert the left one into the right one, or something like that. And that's going to give you worse asymptotics. If you either have to give up the ability to reason about what the ordering is that you're using to make your set go. Oh dear.
Your computer didn't like that plan at all.
Yeah, it fell out completely.
Or I have to give up the asymptotics of insert. It now goes linear in the sorry, n log n, actually. It's not even linear, right? And it's the worst case one. It's not even like insert the smaller into the larger. Whereas the hedge union has very nice properties across the board.
Hedge.
Yes.
You're saying head.
No, sorry.
What's a head union?
So the sort of apology that's often offered is that we could check the two dictionaries for equalities, and if they're the same dictionary, then we could do the sort. Then we could do this faster approach. But now, well, how do I compare two dictionaries for equality? Do I have an eq instance for them? Like, what is the notion of how I compare them for equality? If we're in Java, like every object is equipped with a notion of equality in hash. Great. Sort of. Maybe it's the right one, but maybe I constructed a dictionary for eq of list of A in one situation by using an input, and I constructed the same dictionary in another situation using different inputs. So object equality, pointer equality is not sufficiently fine to actually match them up. But we also have situations where, like, I have a set that's defined. I have like instances that sort of recurse into themselves. So it isn't even well defined for me to be able to compare things for equality, because, like, if I had to sort of explore the instance, I would spend infinite time sort of exploring whether or not this thing is equal to that. So we have cases where you just can't do the check to compare the dictionaries for equality, and you have the sort of, how do you start this problem? Like, so being able to compare dictionaries for equality is kind of a non-starter. Storing a tag, we've already seen, means that you have to store a potentially unbounded number of tags for ideas that may not have existed when you defined the data type. Right? I can make up new classes. Where do you put the tag for a data type or a class you didn't know about? We use monad transformers all over the place. Give me 1 second. And the uniqueness of the monad transformer stack means that I'm not supplying an infinite supply of tags for, well, what monad reader instance am I using? What monad state instance am I using? What, like all of them, the monad foo classes is sort of an open set of things, and I can add such transformers as I go. The notion that we can use dependent types, we've already given lie to the fact that, like, well, I'll just make the dictionary carry around the proof that it is the thing that I want. This actually works for a subset of these classes. There's a I believe it's property-like structure is what they call it in category theory, this notion of if you have a structure that is uniquely determined if it exists, like if you have a monoid, there's one way that you can promote the monoid to be a group. There's only unique, inverses are unique, right? So the mechanism that lets me find the inverse for a given element would be uniquely determined if it's satisfied, right? So you could, if you had a monoid and you had a proof that here is a way to find its inverse, that proof, or the way to find its inverse is uniquely specified. But it's actually an alarmingly small subset of things where the Koch/Agda/Idris approach can actually talk about this is really the only instance for this. And it's only these property-like structures where this holds. And then there's some things where people get uncomfortable around type classes where we say, well, it can't do backtracking. I would like to do this, like if I have an ordering, I would really like to go through and use this more efficient way to nub things together. But if I only have eq, then I have equality, and then I'll use this less efficient way. Like it might be on squared if I have to use the less efficient one, and it's on log n, or actually theta, because given just pairwise equality, you can only do it in omega n squared, and given just pairwise comparison, you can only do it in n log n. But we don't have that. We don't have and one of the reasons why we don't tend to offer that in Haskell is because then if somebody were to introduce an instance somewhere else in the program, it would change retroactively the behavior in code that doesn't even necessarily, ideally it should be able to change behavior in code elsewhere in the program. Right? It's sort of the enemy of separate compilation to be able to do backtracking in this sort of instance search, if that makes any sense. The problem is that I could later on come around and tell you how to do ORD for your data type. And now code that was built and linked and compiled before you ever came along should now start using a different algorithm. Right? So this sort of backtracking in that instance search is like this is an honest problem. I'll say that it's kind of problematic that we can't talk about that nicely. Yes.
If you're going to go and do a global a search to make sure you don't have any incoherent instances anyway.
Well, yes. If you're going to do a global incoherent instance search, there's some things you can say in this space. If you're going to, we now have closed type families that can be used in narrow situations to talk about this sort of thing as well. You can make up a class that is maybe ORD, that is at least eq, but might have an ORD and can tell you whether or not you have an ORD instance or something like that. There's tricks you can play. The one thing that people tend to beat up on this is that they really want local instances. Right? They want to be able to say, I would have an instance in scope that's based on some values that I have locally. Give me the things and let me build the dictionary. And that is a thing where implicits really do tend to be able to shine and say, hey, I'm going to build one. But we have problems. That if you just allow someone to write, like if you, inside of a let clause, let people write instance blah, then you would lose the coherence property that we have. But we can fix this, yes?
What's the workaround? Do you define a new type locally?
Well, so I have a library for this, and it's a dirty, dirty hack behind the scenes, but it's safe. Okay? And effectively, the entire API for the library looks like this. This is in data.reflection. Okay? And what you can do is this. You have reify takes a value and will find a way to make up a dictionary for reify's SA such that I will tell you the S, I generate an S. So since I'm generating a new type, it can't collide with any other type patterns, like types that we had. So the safety of this comes from this for all. And I will give you a reference to the type just so you can talk about it. It's like I don't even actually give you a value. I give you just a dumb data type that has no contents. It's just a way to get a handle on the type. And if you can give me an R based on that proxy, I'll give you an R. And then up here we have the dictionary itself that says, like, if you gave me a proxy S, I'll give you an A. It doesn't have to be proxy. It never uses this argument. It is the ability to get the A out of the dictionary. And the correctness of this is predicated on the fact that this S cannot be any S that's already in your program. So it's generating a new type. So this is just enough information that you can actually make up a local monoid or make up a local instance for your own sort of custom new type.
Do you have an example of using that?
I do.
Like how much boilerplate is that?
It's a pain in the ass.
But it's fast.
Yes. Let's see, here's be an example of a monoid that's custom. So given MAS, S is the parameter, I want a monoid of A's. And here's like the dictionary that we want to have for monoids. We have, the monoid dictionary has mappend and mempty in it, mangled with underscores. And then if we know that S reifies one of these monoid dictionaries for A, then M of A of S is a monoid. And what we do is we use reflection. We peel out the mappend from the thing that we reflected, and we run it. Okay, and here we're literally looking at our result as the value that we're going to reflect upon to get the thing, because MAS, this could be P of S, and I can pass it to reflect. So this is how I would build a monoid for my custom data type. And then here we have some use cases of like with a monoid made out of plus and 0, let's look at mempty appended with M of 2, and it'll go through and compute that sub-expression. So it's not terrible. You have to set up a new type that uses the reified parameter, and you can put anything you want in the reified parameter. And that's enough that you can make an instance that depends on local data. Okay? But it's generative. It doesn't compromise coherence of instance resolution, unlike the more direct approach of just make a new instance and make sure that it's implicit in local scope and this thing will win. So that's the trade-off. And I wish it was a little bit nicer. And I've talked to Simon Peyton-Jones, and we're going to bring this into move the reflection machinery itself into GHC proper, so that there's a little bit better support for it, and it's guaranteed not to break in the future.
That's very cool. I didn't know you could do that at all. So
yeah, it's been a great way to do all sorts of dirty tricks.
It's a little awkward.
And that's really the substance that I wanted to get through. I do think that ML modules are a great thing. They're not type classes. And I do think implicits are an interesting point in the design space, but I think that you give up enough with them that I'm not really happy with the trade-off. Fix that here. And yes, sorry, I completely forgot to get back to you.
Yeah. So when you were talking about the tags,
Yes.
One point that I had heard someone argue with modular implicits with ML, so there's something that some people are working on, is that you only need to have the tag when you have a data structure that relies on some property of that class that you have. Like, for example, when you have the set, when you're constructing it, you're relying on the fact that the two sets share the same order. So you need to supply that order.
Well, with ML, what you've done is you've sort of curried that out to the whole module level. The ordering on A's that you're dealing with for your set data type, for instance, would be curried out to the module level.
Yeah.
The problem then becomes you lose some things there too by forcing that code motion up. Now, how do I take a set of A's and give you a set of B's? Well, I can map it and give you back a new set or something like that. I have to build a one-off combinator. I have to do it in Haskell too, so this isn't a great win in this particular case. This is why it's bad. Set's a terrible example. But like with composition, it becomes more obvious. I can write a non-one-off combinator that lets me map over one half of the composition. Whereas with the set, I have to write something one-off in order to go through and take all the elements of a set, smash it out to a list, something like that, smash it into the new set.
Okay, so even with like the composition type, you'd still need the tag because some of the functions in it rely on the
Yeah, basically the module itself that the set comes from becomes a sort of tag, right, that you can reason about the equality of in the ML style of it. So it's basically a hyped up version of the tag solution with the same attendant problems. That the combinators that you use to manipulate these structures are one-off things.
Okay.
And I find it seems to me that it's fundamentally anti-modular and anti-code reuse, and that's what keeps me on the sort of type class side of the fence there.
Okay.
Anyone else? Yes.
So it seems like you could simulate this whole implicit thing using your proxy machinery. You know, basically sort of like at the outer edge of your program. You know, you just have this. You know.
You pass in the proxy or whatever it is that you want.
Pass in all the instances of all the type classes that you use, right?
Well, you would still have, you'd have to be working on these sort of new type things in the middle and whatnot. The main thing that you get out of it is that within a local lexical scope, right? You have this enforces a. This is actually a little bit stronger of a type than you would technically need. Like if we had a full like linear type system or something in Haskell, if we were in something like Cyclone or something like we could actually build a region or something like that, which doesn't necessarily have to be lexically scoped like this. We can make up a S that is associated with this A, and then it doesn't necessarily have to obey the stack discipline that we have here. Here, if I go to reify something and I go to reify something else, I have to do a reification within a reification. And when I come out and I'm done with one of them, I've used up I've given up the type because it's for all. So you can't quite get away with it in every situation. It has the same problems with like nested regions.
Right. Well, it seems like you should be able to do something like like a monad or something where like at the end of the universe you have like unsafe perform constraints, right?
Well, I mean, yeah, you might be able to come up with a full replacement, but I haven't seen it.
All right.
Yes.
Did you say you argued about this on a lot of Reddits? Are those easy
Yes.
to find?
Probably about 3 months ago, this came up over and over again. And then I said, okay, I'll just do a rant. And I prepared an earlier version of this talk with a few more examples in mind that I've dropped on the floor here.
Okay. One more question. You know Gabriel Gonzalez?
I do.
So I've read a few of his blogs, and it seems like he went on this crusade against type classes. And I was wondering...
I will agree to disagree with Gabriel on this particular issue.
So you guys are pretty much opponents on that issue.
I don't know. Gabriel holds many opinions, and many of them I agree with.
Okay.
Some of them I don't.
Right.
Yes. You're comparing it against the type-safe Scala, right? Because I know a lot of people talk about...
At this point in time, there's no distinction between any of them in this area, as far as I know.
Okay, because a lot of people talk about, oh, if you're in Java when you come to Scala, oh, it's awesome. But if you're in Haskell and come to Scala, it's like, oh.
Yes, I do firmly believe that Scala is a much better Java. I will say that. That I can say without insulting anyone.
But the whole...
directly.
the whole forking of the stack and all that, of the compiler, is interesting. And then they have the whole dotting.
Well, there's the type level fork of it that Miles and those guys have been working on, and then Paul Phillips is
I think the type level that they could get, with that in mind, that they could get away from Java and get closer to this, you think?
I don't know. That's a matter of will, I think. It would be a big change to the language. And I don't know necessarily that, given the constraints of having to run on the JVM, with the type erasure and issues that they have, with the existing culture of using Java-style reflection and the things that they have, if that is even the right decision for a language like Scala. I don't know that it's necessarily the right decision for Scala.
It's like an impedance mismatch.
Yes, there are enough. Scala's trying to do enough weird things on the JVM that it's very difficult for me to say, oh, I should look down from my ivory tower and say, no, you shouldn't do this. What I do want to say is that what they're doing comes at a cost. And as long as we're cognizant of that cost, it's a thing that you may be willing to pay. Anyone else? Yes?
Is there a very brief summary of what is Gabriel Gonzalez's point against type classes?
I don't have it off. I would not be able to do a fair summary of it, so I think that would probably be best found online.
I think you basically said, like, really most of the time you want explicit dictionary passing. Just to make the code easier to read and follow. I hope that's a fair summary.
That explicit dictionary passing.
Then why not just build a record and pass it around?
And that, yeah, a lot of people do, you can do that. The thing is that once you start down that road, it is a all-consuming thing. You never get the pretty type classes back.
Looking at his blog now, the example he brings up to justify this is isomorphism.
Mm-hmm. I think isomorphism would be a terrible thing to build as a class. It's nowhere at all uniquely determined by the two types involved.
Right, but apparently there's no way to do instance isomorphism where you have a tuple of isomorphism A to B and B to C.
I would agree with that. Yes, that is a thing that belongs to the data type. I have lens. I have a whole library full of things that happen to be data types, basically. Or that happen to be effectively composable record-like constructions.
So if isomorphism shouldn't be a type class, why should ORD be a type class? I mean, it seems like the kind of thing that often is not really determined.
So there is a notion that perhaps we this is the art of trying to find the right properties to tie to the type and the right properties that we want to let float around as these values. If ORD wasn't a data type, now defining a new ordering is this big manual process. Now you can make a data type that represents orderings. We can take Ada ordering. You know what? I have one. We go look at my content package.
I feel like somehow the real question is, if you write, x less than y, do you understand what's meant or not?
Yeah.
If not, then it shouldn't be a type class. If yes, then it should, because you know what's meant.
Yeah, we can make a data type for comparisons that says, give me two A's and I will give you an ordering. And then we can define a whole bunch of combinators that are parameterized on the choice of comparison. And we can make a default comparison. We can say, comparison compare. We'll just give you the default comparison for a given number, for a given type A. Right? So here is that data type that we just described for ORD. How often is it that you want to be explicit about that? And when it is the time that you want to be explicit about that, is that the 5% case or is it the 95% of the case? And do you want to make it so that you have to explicitly use custom combinators to glue together individual comparisons to build up your comparison for pairs or for whatever it is you're working with? And you can make the case that for your particular application that you're going to be using these things all over the place. And I have all sorts of nice type classes that let me reason about comparisons, by the way. We have contravariant, because it's a contravariant functor. We have not check-in. We have contravariant forms of applicative that apply to that particular data type, all sorts of crazy things that you can deal with it. You can carve it up and break it out into cases. Now, mind you, those things themselves are classes, so do I give up those classes for reasoning about your data type? Or do I make those things dictionaries as well and now have to go kind of chase after one-off combinator names everywhere? It really becomes the question of what do you want to have to give names to in your application? Do you want to have to give a name to every single ordering or whatever that you're coming along with? Because if that's what you, if you go down that road, you really do look at the ML module approach of, well, here's the ordering that I want to work with here. Here's the thing that I want to work with there. And you have to name all those things. Yes?
It's an idle point there. Yay, even in standard ML, there's one type class, or maybe two, depending on how you like numbers, for eq types. So specifically for equality, and only equality, you can declare a type as an eq type, and then it will do the automatic equality derivation.
Yes.
But not for ordering or anything else. So even there, they said, ugh, you know what, we don't want to have...
We don't want to write the equalities.
Yeah, we compare things for equality often enough that it shouldn't be the name. And that's actually built into the language, not built into a general purpose mechanism like a type class.
Go Java. I'm sorry, ML.
Make everything an eq type. That's ODAS.
Yeah, really awful.
So, yes.
You just went by really fast. When you were talking about isomorphism, you said, "Oh, I've done that. I have lens. Lens is like the."
Well, what lens is all about is making. You have lenses, which are objects, basically, that you can compose together that build bigger lenses. But you can have different lenses. The types don't uniquely determine the lens from one thing to another. I might have, a lens that gets the first half of a pair, or the second half of a pair, or
Talk just on that, on lens talk.
yeah, lens is a very long
He did.
talk.
He did.
I've done talks on lens. They're online. Yes.
By the way, the lens paper in Haskell 10 years ago, 2 days ago got the best paper in the last, 10 years ago paper.
Oh, good.
The one by Nate Foster and Brad Gears and so on.
Okay.
At the Haskell conference in the two days ago in Mumbai, they give a award for.
Oh, for most influential.
Paper from 10 years ago, and we won the award.
All right, I'm really glad to hear about that.
But I think your lens is in the.
My lens and Pierce's
does-
lenses overlap. The ones that I have were sort of come up with by working with Russell O'Connor and whatnot, and what Benjamin Pierce called a very well-behaved lens is the space that the lens library takes and then generalizes and then looks for variations on that. Pierce's lenses go off and start looking at a different kind of lens, which turns out to be more of a computational rat hole in terms of like pinning them down. So we only dealt with the very easy case, and this keeps going on. But the nice thing about the very easy case is that it's sort of completely determined. So it's very easy for you to reason about them just from the laws that you have available. Yes?
Yeah. Going back to Tecmo's thing about not liking type classes.
Mhm.
With Ermine, the first version of Ermine doesn't have type classes.
Yep.
And Ed was able to convince our boss to go in and rewrite the compiler to get type classes. Passing around instances for things like monads and traversables and everything like that
Are absolutely terrible.
Terrible. So there's some cases, like if you've got a, I don't know, you're writing an RPG and you want to have like a monster record instead of a monster type class.
Mhm.
That's reasonable.
Perfect.
A lot of the stuff like monad, you really want in a type class.
I think that summarizes it pretty well, is that things like monad, things that are completely determined, and that you don't want to have to manually plumb, and especially once you start dealing with a big tower of monad transformers and all of the machinery to get down there. You could build monad transformers in the world of ML modules, right? You could do it. Nobody would, and nobody has, and that should tell you something. Yeah, monads are named by their types, yes.
Well, there's strict state and lazy state.
Yeah, strict state, lazy state. We have a few things that are not completely determined. Now the question is the lazy version of that actually a monad? It becomes a question of how strict you want to be about equality in the presence of bottoms.
Writer is another example.
Yeah, writer is another. Anything else?